So we are already familiar with the notion of the rank of a linear transformation. So recall that if T is a linear transformation from V to W, then the rank of T is the dimension of the range of T. Then rank of T is equal to the dimension of the range of T. So recall that this is a very useful notion to have, because this is one of the key ingredients of the dimension theorem, which said that look at dimension of V. If V is finite dimensional, dimension of V is equal to the dimension of the null space of T plus the dimension of the rank space of T, range space of T, which is the rank of T. So rank of T tells us a lot about the linear transformation. So one example would be, let me just leave it as an exercise, or maybe I'll just prove it. Proposition, the proposition states that, so if T from V to W be a linear transformation between equidimensional vector spaces, say between vector spaces each of dimension n, then T is invertible if and only if rank of T is also equal to n. So one direction is quite straightforward. If T is invertible, then in particular T is a surjective map, and therefore R of T will be exactly the same as W, and therefore the dimension of R of T is the same as dimension of W, which is n. So I will just leave that as an exercise. The other part is, suppose if rank of T is n. So observe that what happens when rank of T is n. Then notice that this implies R of T is an n-dimensional subspace of an n-dimensional vector space. Then R of T, I will just write that this directly implies R of T is equal to W, because rank of T equal to n implies dimension of R of T is equal to n. R of T is a subspace of W, and we know that W is of dimension n. And therefore any n-dimensional subspace of an n-dimensional vector space will be the entire space, which means that R of T is W, which implies in particular that T is surjective. But that is not all. Now let us invoke dimension theorem, which tells us that dimension of V, which is equal to n, is the dimension of the null space of T plus the dimension of R of T, which is dimension of W, which is equal to n. So which means that n of T has dimension 0, which means that n of T is the 0 subspace. The only subspace which has dimension 0 is the 0 subspace, which means that T is injective. So what do we know about linear transformation which is bijective? It is an invertible linear, it is invertible. This implies that T is invertible. So we have used multiple results which we have proved in maybe weeks 4 and 5, and it's a good exercise for you to sit and check at what step which of the theorems were used. Alright, so this was just an example to highlight that the notion of rank is a very useful one. Rank also is a well behaved object. So for example, if you take a linear transformation from say V to W, and if you compose it by an invertible linear transformation, the composition or the product of linear transformation and product of composition are just so same notion with different words, right? So you look at the composition of the given linear transformation with an invertible linear transformation, the rank of the composition is the same as the rank of T. So let me just write down a proposition which captures what I just said. So let T from V to W be a linear transformation suppose U, let us call it S, from U to V and Q from W to Z be invertible linear transformations or isomorphisms. So then rank of T is equal to rank of Ts. Observe that S is a linear transformation from U to V and T is a linear transformation from V to W. So this is a linear transformation in particular from U to W. This is the same as rank of QTS, which is the same as the rank of QT. So let us see. Let us try to prove this proposition step by step. Let us first prove that rank of T is the same as rank of Ts. Okay, what does that mean to say that rank of T is the rank of Ts? Rank of T is just the range of T, right? Dimension of the range of T. And what is rank of Ts? That is the dimension of the range of Ts. But what is the, observe that R of Ts is equal to the range of, this is basically, if we write it as T of S of, this is basically T of S of U, right? The set of all elements of the type Ts of small u where u belongs to capital U. But observe that S is an invertible linear transformation. S is invertible. And what is the property of, what is a characterization of an invertible linear transformation? It is a linear transformation which is both injective and surjective. In particular, S is surjective. S is surjective. And this implies that S of U is equal to V. Every element of V has a pre-image under S. This implies that R of Ts is nothing but the R of T, right? This implies that the dimension of R of Ts, which is the rank of Ts, is equal to the rank of T. Okay. I would say that this also indicates this. If T is replaced by Qt, we have essentially shown that, okay, so this also indicates or this implies rank of QTS is equal to rank of Qt. Instead of, so T was an arbitrary map, right? For any T, if you compose it with an invertible matrix, it is going to preserve the rank. So in particular, rank of QTS is the same as rank of Qt. So the only thing that is left to prove would be to check that rank of Ts is the, sorry, rank of Qt is the same as rank of T. Okay. So what is R of Qt? Our next question is to address what R of Qt is. Whatever be the range of Qt, one thing to note is that Q is an invertible map. Since Q is invertible, the dimension of the range of Q is the same as the dimension of the domain of Q. So, this is equal to, I will just write it in a crude manner, Q T of V. Remember that, okay, did I write the pre-image here correct? Did I write it as U? Yes, it is U, it is U. Okay. So, here T is a map from V to W and Q is a map from W to Z. So, T of V is a subspace. So, this is basically Q of the range space of T if you observe. So, Q restricted to T of V will map isomorphically onto its image, right. So, the range of T, but since Q is invertible, so Q of, by dimension theorem, dimension of Q of R of T is equal to the dimension of the null space of Q plus dimension of Q of T of V, which is R of Qt. What is our left hand side? That is nothing but dimension of R of T itself, because Q is an invertible map, and or rather let me put it this way, the right hand side dimension of R of Qt maybe a little more careful, dimension of Q of RT, yes, this is precisely what we should be looking at. Q of RT is the same as dimension of R of T. This is what we can get from the dimension theorem. The previous theorem is just a rewriting of terminologies. This is by the dimension theorem. I will just write it as by dimension theorem here. But then we already know that this is, so I will put a equal to here and tell you that rank of Qt is now equal to the rank of T. So, we have, what have we shown? We have shown the, where did the equality go? Yes, we have shown the first equality, and the last equality was realized as a consequence of the first equality, and that rank T is equal to rank Qt has been proved, and hence all the ranks are preserved. Okay, so let us look at the proposition again. The statement is quite important. What the proposition tells us is that if you consider T to be a linear map from V to W, and suppose S is a invertible map from U to V, then if you compose it with the linear transformation T, the rank of the composition is the same as the rank of T. Same is the case with a matrix Q, not matrix, a linear transformation Q. So, the rank behaves well under composition by invertible maps. Let us now discuss the rank of a matrix. We have discussed rank of a linear transformation already in quite detail earlier. Our goal here would be to define the rank of a matrix and somehow link it to the notion of the rank of a linear transformation. The rank of a matrix, as was noted earlier, is something which is well studied and well understood. So, we will reduce many times the problem of rank of a linear transformation to the rank of a matrix and work with the matrices. So, let us now focus on matrices and the rank of a matrix. Okay, so let A be an M cross N matrix. Then LA with respect to the standard basis, then LA, recall that this is just left multiplication by A in the standard basis. Where is this map from? This is from Rn to Rm is a linear transformation corresponding to A. If you recall what LA was, let me just remind you what LA of X is. This is just left multiplication of the matrix A with the column representation of X. Remember, this was like this, and we did look into many properties of LA. For example, LA plus B was LA plus LB. We also checked that LAB, maybe it was not checked, it was given as an exercise to prove that LAB is LA times LB, and so on. Okay, so given any matrix A, an M cross N matrix A, we can associate a corresponding linear transformation. We are also familiar with the notion of the rank of a linear transformation. We will define the rank of the matrix A to be the rank of this linear transformation LA. So, we define the rank of the matrix A to be the rank of the linear transformation LA. Let us look at an example. So, let A be the matrix 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 0. So, this is a 4 cross 4 matrix, and notice that the rank of A is the dimension of the range space of LA. Notice that I will just leave it as a check for you to notice that this is nothing but the set of all x1, x2, x3, comma 0, where x1, x2, x3 are real numbers. And therefore, rank of A is equal to 3. Of course, in this particular case, it was quite easy to consider LA and explicitly calculate the dimension of the range. But that is not generally an easy problem. It can happen that for say a big M and a big N and more complicated matrix it is far more difficult to compute the dimension of the range of LA. So, we will spend some amount of time and our energy to get hold of methods with which we will be able to simplify this particular calculation. We noticed that if we compose a linear transformation by an invertible linear map or to the left or to the right, the rank of the the rank of the composition does not change. A similar property holds for matrices. So, let me just write it down as a proposition. This actually will just follow from the case we have proved for linear transformation. So, suppose, so let A be an M cross N matrix, B be an invertible M cross M matrix, and C an N cross N invertible matrix. Then rank of A is equal to B is an M cross M matrix. So, this is rank of BA, which is the same as the rank of AC, which is the same as the rank of ABC. Okay, so let us go over the details. What is rank of A? By definition, so let us give a proof. By definition, rank of A is the rank of the linear transformation LA. Is the rank of LA, And how about rank of BA? Rank of BA is the rank of LBA. But if you go back to the lectures 2 weeks back, we did discuss this and we noticed that LBA is LB times LA. This is nothing but rank of LB times LA, because LBA is nothing but LB LA. So, what can we say about LB when B is an invertible matrix? It happens to be the case that we have proved this as well. B is invertible if and only if LB is invertible. B is an invertible matrix if and only if LB is an invertible linear transformation. And by the proposition we have proved earlier, this is equal to rank of LA, since, so let me write down the reason here, LB is an invertible linear transformation. I have written short forms of all of that, but it is self evident. But what is rank of LA? Rank of LA is nothing but rank of A. So, by a similar argument, it is easy to prove that rank of A is the same as rank of AC, and rank of A equal to rank of BA immediately tells us that rank of A is equal to rank of AC immediately tells us that rank of BA is the same as rank of, I have written something wrong here, I am a bit sorry about that, this is BAC, yeah, rank of BA is the same as rank of BAC. Alright, so I will just assume that you will be able to complete the proof here. Idea is extremely similar to what I have just observed. Just notice that LBAC is the same as LB, LA, LC, and that LB and LC are invertible corresponding to invertible matrices B and C. Alright, so this is good, we are in good shape. Okay, so as was noted earlier, it might not be easy to compute explicitly the dimension of the rank of a matrix A when A is a very complicated matrix. Nevertheless, we can still say something. Suppose, so let me just put a stop QED symbol here. So, suppose A is an M cross N matrix. Let us define the column space of A to be the subspace of Rm, which is obtained by looking at the span of the columns of A. So, let me just define it. Or before that, let us try to see, before even we get into what column space is, let us try to see what the rank of A should be like. So, what is rank of A? Recall that rank of A is nothing but the rank of L subscript A, right. Now, what is LA? Remember that LA is a map from Rn to Rm. This is an M cross N matrix. So, Rn to Rm is the map. So, LA, if you consider the standard basis of Rn, then so let E1 to En be the standard basis. Then LAE1 will just turn out to be the first column of A, this is the first column. In fact, LAEI is the ith column, or LAEJ is the jth column of A. But what do we know about LAE1, LAE2 up to LAEN? The fact that E1, E2 up to En is a basis of Rn implies that LAE1, LAE2 up to LAEN should be at least a spanning set of the range space of LA. So, since E1 to En is a basis, of Rn, we have LAE1 to LAEn. This set is a spanning set of range of LA. So, we will call this the span of LAE1, LAE2 up to LAEn as the column space of A, because it is the span of the columns of A, right. As noted here from this, consider the span of the columns of A. What we have just noted is that this space is exactly equal to the range of L of A, and therefore, the dimension of the range space is the dimension of the span of the columns, and that is precisely equal to the rank of our matrix A. Again, we have not simplified our problem much, we have just rephrased it into a machinery or into a language which is obtained from the matrix itself. So, given a matrix A, without going or referring to the linear transformation corresponding to A, we will be able to say that the rank of matrix A is obtained by looking at the column space of this matrix in Rm and looking at its dimension, right. Okay, so let us now get to work to simplify our notion of, we have actually developed all the machinery needed to simplify the notion of rank, not the notion of rank, the method of finding rank. So, we have just noted that if we multiply a given matrix by an invertible matrix, the rank of the product is preserved, or rank of the product is the same as the rank of the matrix A. So, next proposition tells us, and we also know that, okay, I did not explicitly write it down, it is an exercise for you to check that every matrix can be reduced to a row echelon form. This proposition tells us that if a matrix A is in its row echelon form, then the rank of the matrix A is equal to the number of non-zero rows of that matrix A. So, let A be an m cross n matrix in its row echelon form. So, recall that row echelon form, matrix A is said to be in its row echelon form if every row satisfies the following property. Either the row is the 0 vector, or the 0 every entry of the row is 0, or the first non-zero entry of a row is 1 and all entries below in that column is 0. So, you take any matrix in the row echelon form, then the rank of A is equal to the number of non-zero rows of A. Okay, so let us give a proof of this. So, we noted that the rank of a matrix A is not changed after you multiply by an invertible matrix. So, if needed, multiply by the elementary matrices which interchange rows. After multiplying by the required elementary matrices, or multiply by the required elementary matrices, we obtain a matrix with the first, say, k rows, with the first k rows non-zero. So, you get a matrix where A11 up to say AK1, or rather let me not put it this way. Say this is the first k rows and this is say the n minus k rows. It is a 0 matrix here. The n minus k, the last n minus k cross m, not n, m minus k cross n matrix at the bottom is just the 0 matrix. Okay, that is what this means. If needed, multiply by the relevant elementary matrices to get the first k rows to be non-zero. So, clearly then the column space which is the span or the span, so I will just write it down, span of the columns of A, this is contained in, so let me just throw this out, I will not get space otherwise. This particular column space, this is contained in the subspace U of Rn or M, which is given by say x1 to xk and then 0 dot 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 0, where xi's are in R. So, U is basically the subspace of Rm, which satisfies the property that the last m minus k entries are 0. And we know that dimension of U is equal to k, right, since dimension of U is equal to k, we have the dimension of the column space, which is the rank of A, is also less than or equal to k, because this is a subspace of U after all. So, the dimension of this subspace should be less than or equal to the dimension of U. We will show that the rank of A is or the column space will have at least k as the dimension. So, enough to show that rank of A is greater than or equal to k, right. If we do this, we have established that our rank is equal to k. Okay, so let us pick an arbitrary element of U. We will show that it is in the span of the column space of A, and therefore U is contained in the column space of A, and therefore dimension of U is less than or equal to the dimension of the column space of A, which is the rank of A. That means we will get k is less than or equal to the rank of A. Okay, so let x1 to xk 0 dot 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 0 be an element in U. Now, A is in a very special type, it is row echelon, it is in the row echelon form with the first k rows non-zero and the remaining m minus k rows 0. So, let us focus on the kth row. Let C k C1, let us call it C1, be the column of A such that the first non-zero entry of row k or let me rephrase the statement, let C1 be the column of A containing the first non-zero entry. The first non-zero entry of row k. The first non-zero, it is in the row echelon form. So, the first non-zero entry should necessarily be 1, and the definition of row echelon form tells us that every entry below that 1 should be 0, right. So, now define, so let this be V, and let V1 be equal to V minus xk times C1. Now notice that C1 has 1 in the kth row and zeros below. So, xk times C1 will have xk in the kth row and 0 below. V has xk in the kth row and 0 below. So, if you look at V1, this will be a vector as 0 in all the rows below k minus 1. Should think about it for a minute and get convinced that this is the case. Now, suppose yk minus 1 is the entry in the k minus 1th row of V1. So, let me tell you exactly what this means. V1 will be something like, say, something here in the k minus 1th column, it is yk minus 1 and then 0 below. Here it could be anything, at the top it could be anything, but k minus 1th row will be something, let us call it yk minus 1. And let C2, let us follow the same trick as earlier, let C2 be the column containing the first non-zero entry of row k minus 1. Notice that all entries below that 1, the non-zero entry should be 1 and all entries below that should be 0 by definition, and therefore, this C2 has to be a different column from C1, right. It is forced because C1 had a 1 in the kth column, kth row, and that cannot happen here. Anyway, that is not that's certainly being used, and also notice that all entries below the k minus 1th row of C2 are 0. Define V2 to be equal to V1 minus yk minus 1 times Ck, and follow the same procedure. Follow this procedure. After k steps, what do we get? To obtain the 0 vector after k steps. And if we backtrack what we did, we would have written V as a linear combination of C1, C2 up to Ck, where Ci's are columns of our matrix A. This implies that our vector V is in the span of columns of A. This implies that U is contained in the column space of A, or the subspace of Rm which is spanned by the columns of A, and therefore, K, which is the dimension of U, is less than or equal to the dimension of the column space, which is the dimension of the range of A, which is equal to the rank of A, and therefore, we have established our theorem. So, what we have shown is that, so let me show you the proposition once again. If we have a matrix which is in its row echelon form, then the rank of the matrix A is exactly equal to the dimension, to the number of non-zero rows of A. So, let us start with an arbitrary matrix. So, let A be an arbitrary matrix, M cross N matrix, and as I was mentioning earlier, it can be reduced to its row echelon form after finitely many row operations. So, let E1, E2 up to E, say Ek be elementary matrices such that E1, E2 dot 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 ek times A is in its row echelon form. Then the rank of E1, E2, Ek times A is the same as the rank of A, because each of these EIs are invertible matrices, and we just proved that multiplying by invertible matrices does not alter the rank. So, to talk about the rank of A, we just need to reduce it to its row echelon matrix and look at the number of non-zero rows. That will give you the rank of our matrix. But then the row echelon form need not be quite elegant, it might be still bad. We can do even better. Why are we just considering row operations? The column operations will also be multiplication by invertible matrices just from the right, that is all. And therefore, the rank is still preserved if you multiply by matrices from the right. So, let us now observe that we can do much better by considering column operations as well. We can exactly find out a very nice form, or we will be able to derive to a very nice form which will give us the rank, or based on the rank the matrix will be in a very nice shape. So, let us just have a look at that particular statement. Alright, so that is captured in this theorem. So, let A be an M cross N matrix of say rank R. Then we can prove that after finitely many column operations and row operations, A can be reduced. So, then we can say that, okay, let me say that again. Then we can say that after finitely many row operations, column and column operations, A can be reduced to a particularly nice form. Let me just write it down. Then after finitely many row and column operations, we get a matrix of the type, so write it down here, IR, which is the identity matrix of size R. This will be an R cross N minus R matrix. This will be an M minus R cross R matrix, and this will be an M minus R cross N minus R matrix, where 0, well, J cross L, K cross L is the 0 matrix of size K cross L. 0 matrix meaning all entries are 0. So, the theorem is quite powerful in the sense that it tells us that after many row operations and column operations, if R is the rank of this matrix, we can reduce it to this particularly nice form. So, let us give a proof of this. So, after finitely many row operations, let us assume that our matrix is in the row echelon form with the first R rows being non-zero. So, let A be reduced to its row echelon form, and assume that after a few more, if needed, a few more elementary row operations of type 1, the first R rows are non-zero. So, notice that the previous theorem or the previous proposition tells us that the rank of the matrix A will be precisely the number of non-zero rows in the row echelon form, right. The row echelon form will have the same rank. So, yes, it will be exactly the number of non-zero rows, and because R is the rank of our matrix A, there will be R non-zero rows in its row echelon form. So, now let us exchange or interchange rows to obtain the first R of them being non-zero. So, now that means let us call the matrix A prime reduced to its row echelon form A prime. Let me just call it A prime. What is our A prime going to look like? A prime will have something here in the first m minus r rows and 0 in the final, the first r rows it is going to be something, and in the final m minus r rows it is already 0. Okay. Now, let us work more on this, on the matrix A prime. Okay, what do we know about the row echelon form? The row echelon form has a very nice property. After till the first non-zero entry is 1 and every entry below it is 0. So, consider row 1 of A prime. Then let us now do some column operations. What are the column operations? Subtract the relevant multiple. We are doing a column operation of type 3 now to this matrix A prime. And what is, recall what is the column operation of type 3? We subtract a multiple of one column or add one multiple of one column to the other, right? So, addition and subtraction, or we can just add, let me just use the word add. The relevant multiple of the column containing the first non-zero element, first non-zero entry, which is 1 here. In the first row to subsequent columns. So, if say for example, to obtain zeros in the first row. So, if for example, the first row has 1 in the 5th column, 6th to remaining up to n, you subtract the A1k for k greater than 5 times the 5th column, and then you will get all the entries after the 5th column to be 0. Notice that this does not do anything to subsequent entries in the column, only the first column is affected. Why? Because in the row echelon form every entry below 1 is 0, and therefore, this does not do anything to other columns. So, what happens after this particular column operation is the first entry, the first row will have 1 in one entry and 0 elsewhere. Now, repeat the same process to the second row, the same process to the second row. And notice that there will be only one entry which is non-zero, which is 1 in one of the columns, and every other entry now will be 0. And this particular one will be in a different column to the one in the first row, to all subsequent rows, in fact, not just the second row, all subsequent rows. And what do we finally get? We obtain a matrix with every row containing a non-zero element 1 in one of the columns and 0 elsewhere. And these ones are all distributed in different columns. That is what we will end up with. Now, apply column operation of type 1 where you interchange, apply column operations, many actually. Many might be needed operations, or none might be needed, depends on the requirement. Apply column operations of type 1. So, this was all type, remember that these are all column operations of type 3, okay. Right. So, now apply column operations of type 1 to obtain a matrix. So, the first R rows have 1 in one of the columns and 0 elsewhere. So, if you swap or interchange the columns accordingly, we will get a matrix of the type required. Okay. So, if R is the rank, we have a particularly nice way of representing a reduced form of that matrix. So, let me just note what we did. So, essentially we have proved that if A is an M cross N matrix of rank R, then there exist elementary matrices E1, E2 up to Ek of size M and elementary matrices F1, F2 up to Fl of size n such that E1 dot 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 multiplied to A times F1 dot 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 multiplied to up to Fl. This is of the type IR 0 n minus R cross n minus R 0 m minus R cross R 0 m minus R cross n minus R. But notice that this E1, E2 up to Ek are all invertible. So is F1, F2 up to Fl. This means that A can be written as Ek inverse dot 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 E1 inverse times our matrix IR 0. I'll not bother writing the size, it's the same, times Fl inverse dot 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 F1 inverse, because these are all invertible matrices. So, let us call this something, let us call it B, and let us call this something C, and this is precisely what we have proved in the last two propositions. Okay, next let us try to address what would happen if you look at the transpose. We will show that the transpose of a matrix will also have the same rank as A. So, recall that a matrix A, the transpose of a matrix is obtained by reflecting along the diagonal. So, let A be equal to say A11 up to A1n, AM1 up to AMN. Then the transpose of A, what is transpose of A? This will be given by A11 to AM1, A1n to AMN. Notice that this is a n cross M matrix. A few properties of transpose are important to be noted here. Notice that, check that, I will leave it to you again. Notice that you would have seen it already. AB transpose is the same as B transpose A transpose. And further, if A is invertible, so is A inverse, A transpose. So, if A inverse is say identity, let us look at the transpose of this, then A inverse transpose A transpose is equal to identity transpose, which is the same as identity, and that implies that A transpose inverse is equal to A inverse transpose. So, the transpose of a matrix is also invertible. So, now let me give you a theorem which tells us that if an m cross n matrix A has rank R, then so does its transpose. The transpose also has the same rank as A. And how do we go about proving this? It is quite straightforward. So, let us write A by the above theorem. Let us write A in the special form we have. By the above theorem, we have A is some B times I R 0 R cross n minus R 0 m minus R cross R 0 m minus R cross n minus R times C, where B and C are invertible matrices. Now, let us take the transpose of A. Transpose of A will give you by the transpose, it inverts the order in which we do it. You should check that this is the same as IR 0 R cross m minus R 0 n minus R cross R 0 n minus R cross m minus R. This is something which you should check yourself, times B transpose. This is precisely what the transpose will look like. But then if B and C are invertible, so are B transpose and C transpose, and if you multiply by invertible matrices, the rank will not change. So, rank of this gives rank of A transpose is equal to the rank of this particular matrix. Let me just put it like this, I do not want to write it down entirely, but that is precisely equal to R, which is the number of the non-zero rows, which is equal to the rank of A. So, it is not something arbitrary we have shown, if you just think about it, the rank of A transpose will be the dimension of the column space of A transpose, but that is exactly the row space of A. So, the row space of A, if you think about it, is in Rn and the column space is in Rm. So, if you take a matrix, you look at its column space in Rm, suppose it has dimension R, then you look at the column the row space of the matrix A in Rn, that will also necessarily have dimension R. So, these matrices are the relation is being captured well in this particular theorem. Okay, we have spent some considerable amount of time developing simpler ways to look at the rank of a matrix. How do we relate it to the rank of a linear transformation? So, that is going to be our next goal. So, theorem, it is a theorem. So, let T from V to W be a linear transformation. Suppose alpha and beta are finite ordered bases. So, when I say finite, its cardinality is finite, and therefore, V and W are finite dimensional. Suppose alpha and beta are finite ordered bases of V and W. Then rank of T is equal, as a linear transformation we can talk about rank, and this coincides with the rank of the matrix of T with respect to alpha and beta. Irrespective of what ordered bases alpha and beta you take and look at its matrix, rank of T is equal to the rank of this matrix. So, let us give a quick proof of this. It is an elegant proof. We will first define, let phi alpha be a map from V into R n, where n is equal to the dimension of V. Be defined by, we have not defined this map, let us define this map to be phi alpha of a vector V is the column representation with respect to alpha. So, notice that this is going to be a n column in n column, which can be thought of as an element in Rn, and I will leave it to you as an exercise to check that phi alpha. We know that it is a linear transformation. If you look at phi alpha of V plus W, we have checked that this will be V alpha plus W alpha, or V1 plus V2. If you look at it, it is going to be V1 alpha plus V2 alpha. Same with scalar multiplication. Again, if you have not seen it, it is a good exercise to check that phi alpha is not just a linear map, but an isomorphism. Yes, it is an exercise. Similarly, we can also define phi beta. Similarly, define phi beta, which is from V to, now in this case Rm, not V, W to Rm from the image, where phi beta of say a W is the column representation of W with respect to beta. Now, the matrix representation of T with respect to alpha beta tells us that then TV with respect to beta is equal to T alpha beta V alpha, right. This is the impact of going down to basis alpha beta. So, if I had to write it slightly differently, this is nothing but phi beta of TV is equal to, let us look at LT alpha beta, and then this is going to be phi alpha of V, right. If we are to look at phi beta TV as a vector in Rn and Rm, and if we were to look at V as a V alpha as a vector in Rn, then this is exactly what this is rewriting, we get this. Our matrix multiplication is captured by L subscript A, here A is T alpha beta. But let us carefully observe what has happened. This is for all V in capital V, right. This implies phi beta composed with T is equal to L T alpha beta composed with phi alpha, because it is getting satisfied for all V, and we know that phi beta is an isomorphism. This is all, I am not writing down the reasons. Phi beta being an isomorphism, I am just orally telling it, this is equal to LT alpha beta phi alpha. But then what is rank of T now? Rank of T is the rank of the thing in the right hand side here, this part. But phi beta and alpha beta both are isomorphisms, and hence they are invertible, and therefore this is the same as the rank of the linear transformation LT alpha beta, because if you compose with invertible linear transformations, the rank is not changed, but that is precisely by definition equal to the rank of T alpha beta. Okay, so we have now linked the notion of the rank of a linear transformation to the rank of its matrix, and we have spent a considerable amount of time trying to develop all the tricks needed or all the techniques needed to reduce our matrix A into a good form which will give us the rank. So, let me stop this video with an example. Suppose T is a map from P3 of R to itself given by T f is equal to f minus x times f prime. Should check that this is a linear transformation. Check that T is a linear transformation. Now, if you fix the basis 1 x square x cube, x square and x cube. Let us try to calculate what the matrix of T with respect to beta is. The first column is going to be T of 1. T of 1 will be 1 minus x times 1 prime is 0. So, it will be 1. So, it is going to be again 1 and this is going to be 1 0 0 0 because 1 is just 1 times 1 plus 0 times the remaining things. Okay, what is T of x? T of x will be x minus x times 1 which is 0. So, the 0 vector. How about T of x square? It is going to be x square minus 2x square which is minus x square. Right. So, this will be 0 0 minus 1 0 and x cube will be x cube minus 3x square which is minus 2x square, sorry, minus 2x cube. So, this is going to be 0 0 0 minus 2 and this implies that rank of T is equal to 3 because rank of T is the rank of its matrix with respect to beta. All right.